Hello students, today we can see an experiment that is there in your 12th standard. The experiment by using potentiometer. By using potentiometer, you have three experiments. One is to compare the EMF of two different cells. Another is to find the unknown EMF of a given cell. And the third one is to find the internal resistance of a cell. Normally, this experiment is quite difficult for most of the students, especially the circuit connection and the theoretical part of this one. So, if you are watching this video throughout, I hope you will get enough confidence for appearing for the coming practical examination. So, here I will be giving a complete explanation of the experiment as well as a demo, so that by seeing the demo and listen to the explanation, you can get a clear idea about the experiment. So here, the potentiometer is a device. Potentiometer is a device. It is used for measuring EMF of a cell. For measuring EMF of a cell, we cannot use a voltmeter. The reason is that if you are using a voltmeter for measuring the EMF of a cell, for example, suppose I have a cell here. It is having an EMF E and internal resistance small r. If I am connecting a voltmeter parallel to this cell, a voltmeter like this, okay, the voltmeter reading will be always less than the EMF, because when a current flows through this circuit, when we connect a voltmeter like this, a current flows through the circuit. Suppose I is the current flowing, then the voltmeter reading coming here will be V is equal to the EMF of the cell minus I into R, where I is the current through the circuit which flows through the cell and R is the resistance of the cell. So because of the internal resistance of the cell and current flowing through the circuit, a voltage drop I into R will be produced inside the cell itself. So the voltage we are getting in the voltmeter will be less than EMF, that will be E minus IR. So we can never use a voltmeter for finding EMF of a cell, because always the voltmeter reading will be less than EMF by a factor I into R due to the internal resistance small r. Means whenever current flows through the cell, a voltage will be dropped inside the cell itself, and only remaining voltage will be available in the output circuit. But here in potentiometer, when we make use of potentiometer, we are using null deflection method. Null deflection method means zero deflection in the galvanometer. Zero deflection means current is not flowing through the circuit. At null deflection, current flowing through the galvanometer will be zero. So the current flowing through the cell will be zero. If there is no current flowing through the cell, then the factor I into R will be zero. Means if I into R equal to 0, then V equal to E. Means we will be getting the voltmeter reading. We will be getting the value of EMF exactly equal to V equal to E, because there is no internal resistance. This is possible only with the potentiometer, and this is not possible with the voltmeter, because whenever we connect a voltmeter across a cell, a current will be flowing. If a current is flowing, then there will be a potential drop I into R. Because of that, the external voltage will be less than EMF of the cell. So here we use potentiometer for finding the EMF of a cell. Now, the potentiometer basically it consists of a 10-meter long wire. That wire is made up of an alloy called manganese. It is having high resistivity as well as a very low temperature coefficient of resistance. A very low temperature coefficient of resistance means its resistivity will not change with the heating. Its resistivity will not change with the temperature. So when we are continuously using the circuit, the current is flowing through the wire, there is a chance for this wire getting heated up. Due to that resistance, if it changes, then the calculation will be wrong. But when we are using manganese alloy for making this 10-meter long wire, it is having very low temperature coefficient of resistance. It means its resistivity will not change with the temperature much. So we will get almost same resistivity throughout the experiment, and we will get more accurate value. And this potentiometer, it is having 10-meter long wire, this 100 centimeter, then 200, 300, 400, 400 like that. 10 lines will be there in the real potentiometer device. But there are potentiometer with 1 meter line also, but 1 meter length of manganese wire also. But a potentiometer with a 10 meter wire is more accurate than 1 meter wire, because we will get a large area, large length of balancing point. So the sensitivity will be high and the accuracy also will be high if the potentiometer is having 10 meter long wire rather than 1 meter long wire. So here we have a 10 meter long wire, and that is fixed on a wooden plank, a wooden board, and parallel to the wire will be a scale to measure the balancing point. And in the circuit part, there are two sections for this circuit. This is the driver circuit or the primary circuit, and this part is the secondary circuit. The primary circuit, we have to start from the point, suppose I am considering the upper point as A. This point A always I am maintaining positive, and the point B I am maintaining negative. So all positive connection, remember, while doing the experiment, all positive connections should be given to the point A. So here we start with the primary circuit. In the primary circuit, connect a wire here to a key K1 and to a rheostat and to a DC power supply. Here normally we are not using battery, we are using a DC power supply, an eliminator circuit which converts AC into DC. Because we need nearly 4 to 6 volt here, we can maintain this 4 to 6 volt that can be adjusted on the eliminator, and an ammeter. So we started with the positive here, positive of the point A is considered as positive to the key K1 rheostat, positive of the cell is connected here, positive, and negative to the negative of the milliammeter. This ammeter should be a milliammeter, and positive of the ammeter is finally connected to this point. The second part of the circuit is here with the green color. Here we are starting from the same common point A. We have two different cells here. E1 I am considering as the dry cell, the normal cell that we use in our day-to-day life. And E2 here is a Leclanche cell. These two cells positive are connected to this point, same point positive here. And negative of the two cells are connected to a two-way key. There are two-way key with K2 and K3. So two extreme points we are connecting, one end to the dry cell, normal dry cell, the other end to Leclanche cell. The middle of the two-way key is connected to a galvanometer, from the galvanometer to the jockey, J. That is the second part of the circuit. So in second part of the circuit is very simple. All positive connection again we are maintaining at the point A. The dry cell positive is connected to the point A, and the Leclanche cell positive is connected to the A. And negative of both the cells are connected to the two extreme point of a two-way key, and middle of the two-way key is connected to a galvanometer into a jockey, That is the second part of the connection. Now, for comparing EMF, we have to plug the key K1 over here and adjust the rheostat and maintain the ammeter reading. You can keep the ammeter reading, milliammeter reading, between 60 to 80 milliampere. It is advisable to keep the ammeter reading always between 60 to 80 milliampere. For that you can adjust the rheostat, or you can adjust the DC voltage supply between 6 and 4 or 4 to 6 voltage. Just over here and adjust the rheostat. Finally you can get 60 to 80 milliampere in the ammeter. That is the first part of the setup of the circuit. So when we adjust like that, suppose a current is flowing through the circuit in this direction, that is, suppose a small I ampere current is flowing through the circuit. And let small r be the resistance per unit length of this 10 meter long wire. If small r is the resistance per unit length of the wire, and if I is the current flowing through that, then potential drop across a unit length, say 1 centimeter length, will be equal to potential drop across 1 centimeter length of this wire is equal to R into I, or I into R. Where I is the current flowing through the wire and R is the resistance of 1 centimeter, or we can say it is the resistance per unit unit length of the wire. Now, if we are getting a balancing point at a length L, then the potential difference for a balancing length L will be equal to I into R into L. Because for 1 centimeter, balancing point is I into R. For 1 centimeter, the potential difference is I into R. So for an L centimeter, it will be I into R into L. And during the experiment, throughout the experiment, we are keeping I constant, means the ammeter reading should be maintained constant. If you are doing the experiment at 70 milliampere, it should be kept at 70 milliampere throughout. So I is constant and R is the resistance per unit length of the wire. That is also a constant. Therefore, I into R will be a constant. Means we can write this equation. Potential difference is directly proportional to the balancing length. This is the basic principle of a potentiometer. The balancing length will be directly proportional to potential difference. So, in doing the experiment, after making the primary circuit, the driver circuit called accurate, the 60 to 80 milliampere in the ammeter reading, and keeping the K1 closed by plugging the key. And first of all, we can introduce the dry cell, that is K2, plug the K2 here, put the key here, so that E1 will be included. E1 is the dry cell, it is included in the circuit. And move the jockey on either side, and at one point you can see the galvanometer will show zero deflection. At that point, measure the balancing length from this point, that is 100 centimeter. Now we can say this is 100 centimeter, then 100 and suppose this is 160 centimeter. So we can write down the EMF of this cell included, that is E1. It is directly proportional to its balancing length L1. Then remove the key from here, K2, and plug the key K3, so that dry cell is excluded and the Leclanche cell is included in the circuit. So we can say the EMF of the Leclanche cell, if it is E2, it is directly proportional to the new balancing length L2. So one point you have to remember here in doing this experiment, since dry cell is having EMF more than that of Leclanche cell, so if you use E1 as dry cell, EMF of dry cell, then L1 should be always greater than L2. Because Leclanche cell E2 EMF is less than E1. So balancing length of Leclanche cell L2 should be less than that of dry cell. Means L1 should be greater than L2 if E1 is dry cell and E2 is Leclanche cell. Once again, balancing length L1 should be greater than L2 if E1 is dry cell and E2 is Leclanche cell. So from these two equations, we can write down E1 by E2 is equal to L1 by L2. So in the experiment, while doing the experiment, so you have to find the balancing length of first E1, that is the dry cell, then remove the key and plug the key K3 and find the balancing length L2 of the Leclanche cell, find the ratio L1 by L2. You can repeat the experiment, adjust the current here. You can start with the 60 milliampere, take the reading L1, L2, find the value of L1 by L2, then adjust the rheostat, make it 70 milliampere, again get the balancing length for E1 and E2, that is L1 and L2, and find the ratio. Repeat the experiment for the third part of the experiment, that is to find the internal resistance of a cell. There is a slight difference in the circuit. The primary circuit is same, the driver circuit is same. In the secondary circuit, we need to connect only one cell, that is the Leclanche cell. So the positive of the Leclanche cell connect to the point A, negative to a galvanometer, and galvanometer to the jockey. And parallel to this Leclanche cell, connect a resistance box with a key. So here we have to connect a key K2 in series with the resistance box and connect that parallel to the cell. So for doing this experiment, first adjust the ammeter reading by switching on the key here, adjust the rheostat, keep the ammeter reading 60 milliampere. Then without inserting this key here, without inserting the key K2, okay, get the balancing lengths. So if the key is open here, if the key is not inserted, the EMF of this cell, suppose E is the EMF of the cell, that will be balanced by a length L1. So L1 is balancing the EMF of the cell if this key is open. Then insert the key here, K2, and remove some resistance from the resistance box so that a current will start flowing in this circuit in this direction. From the cell, through the resistance box, through the key, a current will flow in this direction, and due to this current flow, there will be a potential drop inside the cell that will be equal to current I into internal resistance of the cell. So the voltage balanced here will not be the EMF, it will be the terminal voltage of the cell, that will be equal to V only. It will be less than E by the equation V is equal to E minus IR. So when we insert this key and include some resistance in the resistance box, we can see here a current I ampere current will be flowing through this circuit in this way. Due to that current flow, a potential drop will be inside the cell, that is I into R. And because of that potential drop, the voltage balanced here at this jockey will not be the EMF, it will be the potential difference balanced here will not be the EMF, it will be the terminal voltage V, that is V is equal to E minus IR. And get the balancing length L2. So L2 will be always less than L1 because L1 is the balancing length with the full EMF and L2 is the balancing length with the V equal to E minus IR. So that L2 will be always less than L1. Then after getting that two balancing lengths, L1 and L2, we can find out the internal resistance R by using this equation. The small r is equal to capital R, that is the resistance included in the resistance box, into L1 minus L2 by L2. And we can repeat this experiment by making the ammeter reading to 70 milliampere and remove another resistance from here. First, keep the K2 open and find out the balancing length for the EMF of the cell. That again will give another value of L1, E proportional to L1. And next, insert the key and find the another balancing length L2 that is proportional to the potential difference of the cell, not the EMF. So L2 will be less than L1. From that two value, we can get another value, another result of internal resistance R, that is R, capital R into L1 minus L2 by L2. But this internal resistance should come constant in all the different trials of the experiment. So do the three trials with the 60, 70, 80 milliampere and find the average value of the internal resistance of the cell. That will give you the internal resistance of the cell, that is the Leclanche cell connected in the secondary circuit. That is the total three experiments. It is there in our syllabus for the board examination. You can see the demo of all these three experiments by using the potentiometer and the real circuit.
Okay, this is the meter bridge apparatus. It mainly consists of a 10-meter length of wire of high resistivity and very low temperature coefficient of resistance. Usually it is made up of manganine, which is an alloy. There is 10-meter length for this one, and there is a scale fixed parallel to this one. Okay, and other components we needed is a DC supply and a normal dry cell, a Leclanche cell, a galvanometer, a jockey, a two-way key, and a milliammeter, rheostat, and a normal plug key. First of all, we have to make the connections like this. I am considering this point, the upper point, as the positive terminal. So there are two circuits here. One is primary circuit, the other one is secondary circuit. The primary circuit means the main circuit, where I am connecting the positive, all terminals of positive terminals to this point A and the bottom point as B. So positive of the power supply is connected to here, the red one, and the negative of that power supply is given to a key. Through the key it is given to the rheostat, okay, the upper part of the rheostat, and from the bottom part of the rheostat it is given to the negative of the ammeter and positive of the ammeter to the other end of the potentiometer. So once again, this is the primary circuit. Here the upper point I am considering as the point A and the bottom point as point B. All positive connections are given to the upper point, point A. So the power supply DC, it is adjusted 4 volt DC. It is connected to the upper point A. The positive is connected to the upper point A. And negative of that power supply is given to a key. From the key, it is given to the rheostat, the upper connection, and from the bottom of the rheostat is given to the ammeter negative, and ammeter positive is connected to the second terminal of the potentiometer. This is the primary circuit. In secondary circuit, we have connected two cells for comparing EMF. One is Leclanche cell. Again, this is the positive of the Leclanche cell. That is again connected to the common point of positive on the point A on the potentiometer. And another one is a dry cell. The dry cell also positive is connected to the positive of the dry cell is connected to the common point A. Positive of the dry cell is connected here at the common positive point, the upper point A, and this is the positive of the Leclanche cell that also connected here. And negative of the dry cell is connected to the two-way key at this point, and negative the zinc rod of Leclanche cell is negative, that is connected to the other extreme point. So dry cell to this extreme point, Leclanche cell to the other extreme point. The middle point is connected to the galvanometer. You can connect either plus or minus of the galvanometer, doesn't matter. From the other end of the galvanometer is connected to the jockey, and this much is the secondary circuit. So once again, in secondary circuit, we have positive of the Leclanche cell and positive of the dry cell. Both are connected to this point, common point A, which is all positive. And the negative of the Leclanche cell is the zinc rod. It is connected to one extreme point of the two-way key, and the negative of the dry cell to the other extreme point. The middle point is connected to the galvanometer. From the galvanometer to the jockey. This much is the connection. So after doing this connection, first of all switch on the power supply and plug the key. Adjust the rheostat to make the ammeter reading nearly 80 milliampere. Okay. Then we can introduce the dry cell into the circuit. Dry cell is connected here. So if I plug this key, dry cell will be included in the circuit. Leclanche cell is not included. And check the deflection in the galvanometer by touching the jockey at two extreme point. So you can see the deflection to one right side, and the bottom of this you can see the deflection to the left side. So if the deflections are coming in opposite side, means the connection is correct. Now move the jockey on the 10-meter line until you get zero deflection point. So here we can see on the fifth line, at one point okay. So here I am getting zero deflection, means at this point, that is 1, 2, 3, 4. So I should count the balancing point from the line point A, 0 of the circuit. So 1 meter, 2 meter, 3 meter, 4 and 5 meter. It is 500 centimeter and fraction is 92. So 592 centimeters. So you have to start counting from positive here. So this one 100 centimeter, 200, 300, 400, 500, and after that 500, the fraction you have to take from the scale. Then remove the key from here, insert to the next point, so the neckline cell is included. Again find the balancing point by touching the jockey at different points and find out the balancing point. So it is getting balancing point here at this point. That is 1, 2, 3, 4, 5. That is 587. 587. Before it was 590. So we got balancing length for dry cell 590, and for balancing length for, once again, balancing length for neckline cell is 580. So we got the two balancing point. If you find the ratio of L1 by L2, you will get the ratio of the EMF of dry cell to that of the neckline cell. So one thing you have to remember here, always balancing point of balancing length of dry cell will be more than that of neckline cell, because EMF of dry cell is more than that of neckline cell. Okay. Now for finding the internal resistance of the neckline cell, the circuit is as before, almost same. The primary circuit, the main circuit is same as the previous case. Only one difference is that only neckline cell is connected to the two-way key. This part is not connected to anyone. Sender is connected to the job key through the galvanometer. First terminal is connected to the negative of the neckline cell, and parallel to this neckline cell, we are connecting a resistance box through a key. So positive of the neckline cell to one end of the resistance box, other end of the resistance box to key, from key again back to negative, that is zinc rod of the neckline cell. There is only difference in the secondary connection. All other connections are as usual in the previous case. Now for starting the experiment, again adjust the rheostat and keep the ammeter reading nearly 80, between 60 or 80, between 60 and 80 milliampere. Then introduce some resistance in the key. First of all, without including, plug the key here and keep the key open. Only the neckline cell is directly connected, and find out the balancing point. Balancing point by keeping the key, which is connected in series with the resistance box, open. So the EMF of the neckline cell will be balanced. Now second step, insert the key. So what will happen? A current will flow through the circuit from the positive of the neckline cell through the resistance box, through the key to the negative. So there will be a potential drop in the circuit due to the internal resistance of the cell, and the balancing point will be obtained not because of the EMF, but it is due to the potential difference, because there is a drop of voltage inside the cell due to the so balancing point is decreased now. It is less than 500 now. So when we introduce a resistance in the box and put the key here, a current will flow from positive through the resistance box through the key to the negative. Because of that, a voltage drop will be there inside the cell due to the internal resistance. So the voltage balanced here will be less than EMF, so the balancing length should decrease. And apply that balancing length in the equation for finding the internal resistance of the given neckline cell. For repeating the experiment, again adjust the rheostat, reduce the current to less than 80, reduce the current less than 80, like 70, and remove another resistance from the box. First keep the key open, then find out the balancing point. Okay, then after that introduce the key here in the which is connected in series with the Lagrange cell and the resistance box. Again get another balancing length. Now repeat the experiment for one more value of current by adjusting the current in the ammeter 60, 70, 80, and we can find the average of that. It will give the internal resistance of this Lagrange cell. Okay.